to also show some more edit tools that are available.
Yes.
Okay. Okay, then first what we'll do is the drawing that I've shared for today.
Yes. Yes.
Okay, we'll start with the modeling of that structure first.
Okay.
I
Okay.
had not shown how to model shear walls in the last class.
Yes.
Right. So today what we'll do is we'll define a shear wall
Mm.
and model a building with a shear wall.
Mm.
Okay, and then I'll show some other edit commands that I had skipped in the last class.
Okay.
Okay. Okay, then I'll turn on my screen now.
Yes.
Okay. Then. So this is the new building that I've shared, the new building plan.
Okay.
It is similar to the previous building. Okay, with only one change that there is a shear wall.
Yes.
Okay, there is a lift coat that will be modeled as a shear wall over here. Okay, and there is another thing over here. We have a circular column.
Okay.
There is the C4 circular column over here.
Mm.
Wait, I think that C4 is there in the other problem that I shared, or that's for
Homework problem.
homework. Yeah, it's for the homework problem. Okay.
Here
So,
C1 is L shape, no?
yeah, there
Here
is
we
an
have-
L-shaped column here.
Yes.
So we'll work on that as well. We'll be using the section designer to model this.
Mm.
All right. Okay, so let's start. So section designer also was skipped in the last class.
Yes, section designer.
Yeah, it's a little advanced. So
Yes.
okay. Okay, so we define a new model. Change the built-in settings to metric SI. The region for default materials India. Steel section database will also be Indian. Okay. All right. So we'll go to custom grid spacing. Right. We have first we'll define the alphabetical grids that is along the vertical axis, the y-axis. Okay. So A is 8, B is 8. I'll not be modeling the the secondary beams. I'll not be using grids this time. Okay. So I'll just go with the primary beams and the columns. So A is 8. This is also 16. It is 8, 16. 24, 32. So I'll just add another one here, 32. Okay. And then starts from 5. So this will be 5, 4, 3, 2, 1. We have 8. This is 30. 3.300. So for the story data, I'll be keeping the founding depth at say 2 meters. Typical story heights of 3 meters each. And I'll be having another fifth story over here. There will also be 3. Okay.
Maybe we can wait for students to complete till here.
Yeah.
So all of you can come out till here. Story data you can complete. We are having 5 stories. Founding story is 2 meters, and then rest of the other stories are 333 meters. As last class we did, copies paste a story.
Mhm.
So total 40 meters height you will get. And then press OK. Hope you guys are able to follow. Grids have been given to you. We have not modeled in between grids. We have only models. Main ABCD grids and 1, 2, 3, 4, 5 grids. And we have given 5 stories to that. Are you able to make till here? Okay, Anish, let's move ahead.
Okay. So the L, the only thing different in the columns here is the L-shaped columns. Okay. So we have L-shaped columns, which is 600 mm by 600 mm, and the thickness is 300 mm. So we need to model this time. This will be different. Okay. So before we do that, first we need to define the materials over here. We go to the material properties. This is the sequence that will follow for modeling any structure. We go to the, we'll first define the grids, then we'll define the materials that are being used. For an RCC building, we'll be having concrete, and we'll be having rebars. So I'll define M25 grade of concrete, having weight per unit volume 25 kilonewton per meter cube, and the modulus of elasticity and the Poisson's ratio, thermal coefficient of thermal expansion. These have already been taken up by the program. Okay, now you can check another thing over here, the design property data. Okay. So we have 25 MPa concrete over here. Okay. So if it's lightweight concrete, we can model that as well. Okay. So I define the concrete first. The next step would be the definition of the rebar. So I'll go to rebar now. Select the suitable grade of rebar, and then press OK. So this window pops up now, showing us the properties of the rebar materials. You can check the design property data from here. It gives us the codal values of yield strength and the minimum tensile strength, expected yield strength, and the expected tensile strength. So, okay. Now we have defined our concrete, and we have defined the rebar material. So I'll close this window. I'll press OK. And the next thing would be to define the frame sections. So we'll go to section properties, and then frame sections. We'll go to add new property. Now we had seen the column was L-shaped. This dimension was 600. This dimension was 600 and the width is 300. So I'll go to add new property. Now the section shape is concrete rectangular, but I'll be using a special type of cross section. So I'll be using section designer for this case. Now in section designer, the property name I'll keep it as this window that pops up here. It shows us different data that will be stored here. That will like the property name, base material, then the notional size, the display color, and what type of design it will be. So property name will be L, since it's L shaped. 600, I'll go with LC, L column. 600, so 60 centimeter by 60 centimeter by 30 centimeters. Okay, so initially I'm keeping the design type as no check or design. Okay, so I'll open the section designer now. Is everyone following?
Yes, you can go ahead, please.
Okay. So now in this section designer, another drawing window pops up, which is in the form of a graph sheet, which is divided into 500 blocks, and these 500 blocks are again further subdivided to give us a sense of the size. So now what you'll do is, we see here a lot of drawing tools available to us on the left hand side. Now the fourth one here, the draw concrete shape, I'll come to draw rectangle. Okay, and I'll press at the intersection of the X and the Y axis. Okay, a rectangle is formed now. Now the dimension of this rectangle is currently 600 by 600. To open this pop-up window, what you need to do is do a right click of the mouse on the shape and it pops up. So this is a rectangle one. The material is M30. You can change it to M25. And so what we have is the height will be 600. The width will be 300 for our L shape. So what I'll do is first I'll draw this part of the L, and then I'll draw this part of the L. Okay, so height will be 600 and the width will be 300. So currently with the rebar, I'm keeping it as no. Okay. So we have a rectangle now, which is 600 by 300. So the next step would be to draw this outstanding leg of the L-shaped column, which is 300 by 300. So I'll again go to this draw concrete shape, click on it. Okay, we can go to draw rectangle, then press here. Another rectangle is formed. Select it and do a right click over here. Change the material type to M25. But this will be 300 by 300. Okay. Right. Now, if you zoom over here, what you see is now a rectangle is superimposed on another rectangle. This is not the L shape that we are looking for. So what we need to do now is select the smaller rectangle, and just like the previous main window, we have the file, edit, view, draw, select, and display tabs over here. There is a replicate command here as well. So we'll go to the edit. Okay, there is a replicate command over here. Now, what I need to do is I need to move this block from here to here and then bring it from here to form the L shape. Okay. So what I'll do is I selected the inner block already. I need to offset it by 600 mm. Sorry, 300 mm. So I'll do this. The X direction increment will be 300, and I'll delete the selected object. Okay, so it has come here now. So the next step would be to again go to edit, replicate. We'll be having another 300 mm in the along the y-axis. Sorry, 150. It will be 150. Okay, I'll go to edit, go to replicate. This will be 150. Okay, so we have formed the L shape now. But these two are again different sections. We need to change it to okay. So we have formed an L section using the replicate and the draw rectangle command. Okay. Now there is I have done this on purpose just in order to explore the section designer. Okay, we actually have predefined L-shaped profiles over here as well. Okay, but there are certain complex shapes which there are some predefined shapes already given here, like we have the T, then L, a box, a pipe, then cross. But certain shapes need to be modeled using these replicate and delete commands if it is not available in this list. Okay, so what I'll do is now I'll press the escape. I'll delete whatever I've done over here and go to draw L shape. Okay, so the L shape is drawn now. Now I need to give the dimensions of the L shape. So I'll left click on the shape, gets selected, then I press the right mouse button. Okay, so the material will be M25. The height will be 600. The width will be another 600. And the flange thickness and the web thickness will be 300 each. Okay. And it has no reinforcing currently. So I'll press OK. So we have the L-shaped column as per our definition. So as per our model. Is everyone following? Hello.
Yes, Anvesh.
Okay. Okay.
You can go ahead, please.
Okay. This L-shaped column has been defined now. I'll press OK. The base material was M25, so I'll make it M25. And currently I'm keeping no check or design the tab. So the section that we defined just now, We can view the section properties from here. We have the cross-sectional area, then we have the shear area for axis, for local axis 2, local axis 3. Then we have the moment of inertia about the local axis 3, the moment of inertia about local axis 2. Then we have the product moment of inertia about 2, 3 axis. Then we have I major, I minor, all the properties here are listed. Then I press OK. So we have defined the L-shaped column that will be coming over here. So now quickly what I'll do is I'll define the other two columns that we have here, that is C2 and C3. These will be 300 by 600. So what I'll do is I'll make it concrete rectangular. Go to concrete, select M25, column size C30 by 60. Depth will be 600, width will be 300. Okay, I'll go to the modify rebar. Now design type is column. The longitudinal bars will be HYSD 500 and confinement bars will be 415. Now, these things here, currently I'm not going into too much of a detail over here now. These things will be taken up while we design. Okay. So currently, let us focus on this part. Okay. All right. The other column is C 500 by 500. So add new property, go to concrete, C 500, C 50 by 50. The material type will be M25. Go to the modify show rebar, EM2 and 3 design. The longitudinal bars will be HYSD 500. And then press OK. So the column sections have been defined now. Let's come to the main beam sections, the main beam and the primary beams. This is similar to what we had done earlier in the previous class. You go to concrete. This will be the main beam, 300 by 600. Grade of concrete M25. Depth will be 600. Width will be 300. Now for the modify show rebar, we need to change it from column to beam. The longitudinal bars will be HYSD 500. Confinement bars will be HISD 415. Let's keep the cover to 30. Okay, so primary beam has been defined. Now, while defining frame sections, we can make use of the options here as well. There is an option of add copy of property. So like if we have like when we are defining multiple columns, say, instead of going into the rebar properties each time and changing them from column type to beam type, what we can do is, say we are defining columns, we'll select a column section and make an add copy of property. So what happens is it creates a copy of the section that is already defined here. So this can be used for defining the materials at a quicker pace. So we have a primary beam defined here. So what I'll do is I'll do an add copy of property. So we have a copy of the 300 by 600 beam that we had already defined. So I'll name it as SB 230 by, I think it was 500. Yeah, 500. So depth will be 500, width will be 230. Okay, now can check everything is fine. Okay, all right. So we have defined the frames over here. Okay. So next step would be defining the slabs, the flow slabs. So again, come to section properties, slab sections. I'll go to add a new property. Now we have, say, S150 of the grade M25. The modeling type will be membrane again, and property type will be slab. Thickness will be 150. So now this thing that I had done up till here, this was done in the previous class as well. Okay, so now next thing will be a little different. Okay, now we'll go to define section properties. We'll go to the fourth option, that is the wall sections. Okay, so this wall properties menu pops up. What I'll do is, now see, every menu has this add new property and add copy of property option available. If there are multiple sections, then we can use add copy of property for faster definition. Okay, and if you need to change the properties of a particular section, we'll have to use modify or show property. So what I'll do is, I'll instead of I'll just first I'll do is add new property. So wall property data pops up. The wall property name is wall2. I'll change the name to lift wall, and the dimension was, I'll measure it from here. The dimension is 230. So we have the wall material will be M25. Property name, I'll keep it as LW2230. And now here, the modeling type will be shell thin, because we'll be using the both the in plane and the out plane bending of a shear wall for the lift core. This won't be membrane. This will be shell thin. Okay. Now, if we have, say, squat shear walls of very less height and large thickness, then we can use shell thick to capture the shear deformations as well. Okay. So currently we don't have a squat shear wall, so we'll be using shell thin. All right. And the thickness will be 230. Okay. All right. So we have defined the wall section over here. So I'll press OK now. Right. So first now let us draw the column sections. I'll start with here. Start with grade 5. Okay, quick draw columns. Property will be C 300 by 600. Okay, I'll turn on the all stories option over here and make a window. Okay. Now to change the column orientation, we'll rotate the local axis by 90 degrees. We'll select them. Now to rotate the local axis, we'll go to the assign menu, go to frame, and then the local axis. So rotate angle by 90 degrees. Okay, so you see that the axis 2 and the axis 3, they have been rotated. Okay, so to remove the local axis from here, I'll press the show undeformed shape button over here, or we can also use shortcut for F4. Okay, the next row of columns will be C2, C3, C3, and C3. So we have this over here, and then 500 by 500 in the other 3 grids. Again, this will be rotated by 90 degree. So we'll do the same exercise again. Go to assign, go to the second option frame, and go to the 6th option local axis. Rotate by 90 degree, press OK, and clear the local axis. Okay, next step is grid 3. Now in grid 3, we have the L-shaped column. The modeling this column will be similar to the other columns. The only thing different will be the orientation. We need to match the orientation as per the drawings. Okay, so we have this one here, and the square column here, and we have the L-shaped column over here. Okay, so you see that the L shape is currently not oriented properly. What we need to do is the same exercise. Select this, go to assign, go to the second option frame, go to the 6th option local axis. Now we need to rotate it by 90 degree, but in the negative direction. No, sorry.
Positive 90.
Yeah, positive 90 degree. Okay. Yeah. So next we'll be modeling this. Then we have a square column, another rectangular column. So we'll change it from here, make it square, and then we have the rectangular column. Then we have the L-shaped columns again. So we'll select LC. Okay, this has already been oriented. We can change the angle from here also. From the properties of object, moment releases, angle degree. Okay, another column is remaining. This is the rectangular column. Okay, so finally we'll again check the orientation. These columns are not oriented properly. Then this column as well. And these 2 columns need to be drawn. So we'll change their orientations now. Go to assign, go to frame, go to local axis, rotate by 90 degrees.
Yes.
Okay, so our columns have been created. Right. Okay, so then check the 3D. It's available in all the flows now. All right.
3D excluded you show, maybe that will be better.
Extruded view, you can see it from here.
Because LV they will be also see now.
Okay, L over here.
Yes. Three columns, 1, 2, 1, 2 on initial first grid and third on third grid.
And then here, and then we have.
And shear
Okay,
wall
so
we are not.
yeah, now we have to
That
model
we-
the shear wall. So we'll go to the plan view again, story 5. Okay.
Do we
all-
have to do arrangements because the center line is at A?
Yeah,
and
yeah,
in
yeah.
the drawing we are seeing.
Yes,
That
yes,
will do.
yes. That will do. We'll do
Offset,
that. We'll do that. We'll do that. We'll do that. Yeah.
offsetting it. Okay.
Yes, yes, offsetting it. Yes, correct. Okay. So fine. Okay, now we need we will do is what we'll do is model the shear wall now. Okay.
Till columns,
So-
anyone has any issues? I hope everyone has understood how to make a column which is not of a general shape. Any shape you can create in Section Designer, even a rectangular column you can create in Section Designer. But those shapes are available directly to you so that you can directly make, and Section Designer, other things are clear, I hope. And wall section, how to make. If any doubts are there in those, please raise your doubts so that before moving ahead to model the wall, those doubts are clear.
No sir, not yet.
अभी बना रहे हो शौर्य?
सर मैंने इंस्टॉल कर लिया है सॉफ्टवेयर, वो मैंने प्रीवियस वीडियो देखी थी कल.
ठीक है, तो आप बट अभी जो देखा उससे बना पाओगे ना, यहाँ तक आगे बढ़ पाओगे?
यस सर, मतलब समझ पा रहा हूँ मैं थोड़ा थोड़ा. मैं इस वीडियो को एक बार फिर से गो थ्रू करूंगा.
ठीक है, आगे फिर देख लीजिए. अभी आपने शुरुआत ही नहीं करी है तब तो बहुत पीछे हो आप आज का सेशन. तो आप देखते चलिए, फिर जैसा वीडियो को साथ में फॉलो करिएगा.
ओके फाइन.
एनीवन एल्स एनी डाउट? और किसी को कोई डाउट हो जो अभी तक?
No, sir.
ठीक है, चलें सर. Anvish, we can go ahead.
The last 15 to 20 minutes you can keep for the doubt sessions.
Yeah.
Okay. Yeah. So now we need to model this shear wall over here now. Okay. So shear wall is 4 meters from grid 4. Okay. The height in plan, this is 4 meters, and the width in plan is 2 meters. Okay. So what we need to do here is now we'll be exploring the draw wall command. Draw showed all wall objects. Now we'll go to draw walls in plan. Okay. So now here the type of area will be up here, and the property will be that we have defined, say LW230. So this drawing tool is actually like the quick, like this, the draw beam or column command. You can just simply use this to draw walls. Okay. So we need a specific height, a specific dimension. So for that, what we'll do now is we'll draw a joint object. The y of so the length along y-axis will be 4000 mm. So it's like this, and the width was 2000 mm. Okay. All right. So we have the outer portions of the wall over here now. So I'll again use draw walls in plan. This command is available here as well along the left ribbon. Now I'll use the grid and the joint to draw the walls. Okay. Right now, I think there is a boundary element kind of thing over here of 460 mm dimension. So what we'll do is we need to measure the center line dimension from here, from the center line of this leg of the wall to the outer edge. This is 345. As we are measuring, as we are modeling all the objects along the center line. Okay, this can be seen in the extruded view also. See, so we'll again go to draw joint objects. We have offset in the y direction of 345. Then again 345. Okay, so we'll be again using the draw walls in plan.
So this is just offsetting a joint,
Yes,
or we can create a simple line object also and then offset along that.
yes, that can also be done. We can use joints, or you can use line objects. When you use line objects, it's better to use the none. There is a property available over here of the type none. It's better to use that. So if you use that, it won't be a problem. It won't create problems in the analysis results in case you forget to delete them afterwards. Okay. So now here we see that the lift code has been created. Okay. You can see the 3D view also. The lift code is there. Right. Okay, so now we'll come back to the plan view and create the beams.
So in the wall, we are not giving reinforcement.
Wall may, no, currently I'm not going into the design aspect. I'm just showing the analysis. While defining, we don't define the.
As in column, we define beams. We define.
Yes. Yeah, in beams, we are not defining the rebars.
Before the
analysis.
Yeah, in beams we are just giving that this steel will be used, this much dia will be used.
Yes. This will be done when we use when we'll be using this command over here. When you go to design, okay, there is this shear wall design. Over here, there is this
preferences options.
Yeah.
Yes.
Okay. Actually, the rebars that we are defining for beams as well as columns, it won't be used. It will be used in the design. It will be used in the design. In the design phase only.
Yeah. So in design phase, they will, if they are changed, then it will give the changed solution.
Yes.
If they are not passing the minimum bars which we have given.
Yes. We can do that. We can check whether the bars that we have given, those are adequate or not. We can check that as well. Or we, in the form of demand capacity ratios. Okay.
Yes.
Or we can
in columns also
have new. Yes, even for columns.
Yeah.
Even for columns.
We can even go without defining the rebars initially.
No.
In columns, we have to.
No. You have to define it. Okay, because you're like when you're analyzing it, that time it won't make much difference. Okay, but when you go for design, that time it will be different. Because for columns, the program has to create interaction diagrams. So we need an assumption in the beginning. For beams, that is not mandatory.
All right.
For beams, say we need to check the design of one particular of some of some beams for a project. So we can define like if you have noticed, I think in section properties we have frame sections. Here this if I open this beam thing over here, modify show property and go to rebar, you see that reinforcement area overrides for ductile beams. They are provided over here. So you can use this, or else you can. But these are mainly used for nonlinear analysis, like when we are going for, say, this plastic hinge determination. Okay, in the frame elements, and that time we define this.
Okay. All right.
But normally, yes. But normally, what we do is we will not be defining anything over here. We'll be taking the design that the software gives.
So design does it gives like RCDC gives us the drawing, or it only gives the demand capacity ratios? It can give us.
We'll see that. We'll see that. Otherwise, we'll digress. If I just go into this design thing right now, we'll digress from the main topic. Okay, because seismic analysis, a lot of things are remaining.
Yeah.
Please, so I need to. Yeah. Okay. So now what we'll do is we will make the beams, the primary beams, right? So I'll use this quick draw beams columns, and the property will be the primary beam that we have defined, the main beam, 300 by 600. I'll make a window. Again, I'll make a window. I'll make a window over here as well, and the primary beams have been defined. Okay, now a word of caution for. Okay. All right. Okay, fine. Okay, so it has been defined now, the primary beams. Now for the secondary beams, I'll be using the replicate command. Okay, so this secondary beam is 2 meters from the primary beam at grid 1. So I use the replicate command from here. I'll go to edit, replicate. This is 2 meters. Okay, fine. Then this is also 2 meters. Okay, then this is again 2 meters along X direction. Now, if you feel that your frames are not getting selected, you can always check here. While working in the extruded view, it may not be visible clearly, so you can always check here if your frames have been selected or not. Right. Then we'll go to the other ones. This is 3.2 meters from grid C. From grid C, it's 3.2 meters. And this is from this leg of the. I think this is a primary view. Let me check. Yeah, it's a primary view. Okay, so we have modeled all the secondary beams. Only one primary beam is remaining for the shear wall.
How come they have given primary beams not between the columns? They are just in between, lying between primary beams. This 300 sections is they have given.
Where?
This beam which you are modeling is with the beam just you model, na? It's not between the columns, na? Primary beams
it's for the shear wall.
Yeah, it's for the shear walls. That's why the size they have increased.
Yeah, right. Okay, so now I'll turn off the extruded view. Okay, we'll select. Okay, now see this thing again. This, since I was working in the extruded view, it has not reached up to this line over here. So I'll again, like in the previous class I had mentioned, I'll make use of the aligned
Extension.
joint subframes. Yeah, I'll
Mm.
extend it. Okay, fine. So I'll assign the frame releases. So I'll go to assign, second option frame, and then the third option frame or releases. Partial fixity. Yeah. So I'll release them now. Okay. Okay, so fine now. Now, when I turn on this extruded toggle view, you can see how the framing is happening.
Mm.
Right? You can see how the framing is happening. Okay. You'll see over here that the beam is being framed into the column from the outer edge. All right. But typically what happens is we have this, what is it called? We have the center line modeling or ETABS.
Yes.
So it is going directly into the center line. So we need to define some offsets. And before we go to this offset thing, okay, we can define offset over here, but there has to be a proper transfer of the forces from the beam to the column.
Mhm.
Okay, so what ETABS recognizes is like it recognizes the center line technique.
Mhm.
Okay, so if you have an offset, say if I offset this beam from here to here, it may not recognize the beam to be joining to the column. So we need to define a rigid link. Okay, that will transfer all the forces from the beam center line to the column center line.
Okay.
Okay, so okay, I'll give a small little example over here as well. So currently we have the beam over here, which is at the center of the column, right? So this beam width is 300 and with the column width is 600. So we have over here 150 and we have 300. So we have 150 ka gap over here.
Offset. Mm.
So we need to define offsets, right? So I'll turn the undeformed shape over here, select this beam. Okay, I'll go to assign. I'll go to assign, go to frame. Okay, and there is this fifth command over here. Okay, the insertion point.
Okay.
Now insertion point, we have we can specify offsets over here. Frame joint offsets from cardinal point. Okay, cardinal point is the point where we are intersecting intersecting the elements.
Okay.
Okay, so we have now this is the axis, the local axis that we have, 1, 2, and 3. 1 is actually the axial thing. Okay,
Mm.
3 is the axis along the depth.
Mm.
Okay, and 2 is the axis along the width. Okay, perpendicular to the width. So here what we'll do is we'll be having this offset along the axis
Axial.
3. No, not axial. Axial is along this.
Okay.
Along the
For beam we are
that
doing offset, not for the column.
not for the column. We'll be doing it for the beam.
Beam.
So I'll go
Yes.
to, I turned it off again. I'll go to frame. I'll go to insertion point. Okay. Now 3, I will be say taking an offset of 150 at the end J. And now end I and J. How do we see end I or J? All right. So to recognize this ends I and J, we need to select the beam. Okay. The beam information tab opens up. We'll go to geometry. We have end I, that is at joint 1, and end J at joint 6. Okay. So what I'll do is I'll select this joint. By selecting, I'll need to press the right mouse button. We have joint 6. Okay. So joint 6 is end J and this is end I. All right. So this is end I, and this is end J.
J.
I'll go to assign, go to frame, insertion point. Okay, I'm just giving some values to check,
Positive should be minus.
and I'm just checking once.
Yes.
Okay. Okay. So you see that the beam has been offset now.
Yeah, it has come to
Yeah, it
the
has
wrong
come to
end.
the other side. Yeah, it
Yeah.
has come to the other side now. Okay. So here you see now the center line is there already.
Hmm.
Center line is there along the center line of the column, but the
Columns.
beam has now been extruded.
Hmm.
Okay. So what we need to do is we'll be having, we'll make it 0. And make it minus 150. Okay.
Hmm.
So we have this thing now over here. All right. Similarly, we can offset this as well. Okay. Then we have this also, which is an offset.
Both of them. Above one also.
Yeah, that one also. Yeah. So this is how we go about with the thing. All right. Now, in some cases, we might have a column. Okay, where the say even by doing this offset, we are not being able to, have the beam center line on the column center line. In that cases, we need to add rigid links. Okay, that I'll show you maybe at the end of the training session. Okay, the link part of thing that I'll show you at the end. Okay, so this is a simple structure. We can go out with the offset command. Fine. So it is.
But here we are modeling, say, the column at joint A, which we are seeing for say 150 mm on 150 mm. Beam is also modeled, column is also modeled. So 3 times the material is coming at the joint.
Yes. Yes. But actually, for analysis wise, okay, when we'll be doing the analysis, actually the beam element and the column element will be separated at the junction.
Do we need to give some property modifier for this or any
We
other
have this.
command for this?
Typically, it is already taken, but there is this command over here, frame. This is end length options.
Yes, end length offsets.
Yes. Okay, so we can automatic from connectivity. Okay, this option, or we can have some defined lengths, or we can add a rigid zone factor. Like
What
if we
is
know
this?
the rigid zone factor will be in the sense like say you have your column and you have your beam. Okay, the ratio of the beam and the column widths from the center line. Okay, like the column width from the center line, that by your beam cut depth, you'll be getting a factor. You just put that factor over there. Okay, the bending moment diagrams and the shear force diagrams will be shown only for
that much
the remaining portion.
Remaining length.
Or else you can give manually. Say end I and end J, you can give manually.
So this is the offset only. So if it is say 100 mm or 150
this is not for offset. The thing that I had done earlier, that was for the geometrical offsets. Yeah, shifting. Okay, but say when we'll be checking the bending moment diagrams, say you want to just take the analysis.
It will come 75 mm here, no? It is total 300 mm depth, no, of the column.
Yeah.
So here it will come 150 mm, which is overlapping.
Yes. So what
This
we'll
beam
do
is
is
overlapping 150.
yeah. So this is the rigid zone over here. So we need to
Yes.
give an offset over here. Say this will be 150.
Yes.
Okay. And here again we'll be having 150. Okay.
Hmm.
So beam wise, say if the beam is framing into this column,
Hmm.
okay, this beam is framing into this column along the width. So
Hmm.
we have 150 ka rigid zone over here.
Hmm.
So here the end offsets will be 150. But in this case, we will be having some other end offsets.
Yeah.
Or in this
That we will
case,
find out.
yeah,
Yeah.
that say if you are wanting to use the results,
Hmm.
only the analysis results from the software for some design.
Hmm.
Okay, so at that time we can define this offsets over here.
End offsets. So that
Yeah.
bending moments and shear forces come as correct.
Yeah, the bending moments will be shown from the column face.
Okay, from the column.
Okay, not
And
from
if
the
we keep
center line of
automatic
column.
connectivity, yeah, if we keep automatic connectivity, then it will show from center
It
line.
will be from the center lines.
Okay.
Okay, but for when the design will be carried out, that time it will automatically take up the forces from the faces.
From the first phases. For
Yes.
design, that will take from
Yes.
there. All right.
Yes.
All right.
Okay. So since we are doing the offset exercise, I'll not waste too much time in doing the offset exercise now. In fact, I'll give that as a homework.
Sure.
Okay, for the model for the drawing that I've sent. Okay, in
Homework
that while modeling that, I would ask the students to use the offset command.
Sure.
Okay, yeah. Okay, now before I need to carry on with this model. This is having. Okay, now the slabs need to be created. So I'll go to story 5. I'll make rectangular slabs. S150. All stories option is working, so it will be automatically modeled everywhere.
Then you have to delete from the list.
Yes. But I think in this version, this is not coming in.
Directly take care.
Yeah.
This is 22.5. Okay. We
Yeah,
are using
21.
21.2.
Okay, then I think you need to delete. Okay,
Yeah.
because let me just check once. Okay, no, it's coming. It's coming. The frames earlier used to come, so that is not coming in this version. But yeah, the slabs are coming. Okay, so when we delete the slabs from the base, we need to turn off the all stories option. Otherwise, everything will be gone.
If I'm selecting object, how to make sure that frames are not selected?
Okay,
Just we have to be in between. Make sure that frames are not selected when you are selecting like this.
Okay, you want to select only the say. Actually, here we don't have some what is that called? This
plate cursor kind of thing.
Yeah, plate cursor or the frame cursor kind of thing. But here we have the select command window. Okay, so you can go to the select command. Then you can say select object type. Okay. Now say you have selected some frames while selecting the slabs. So you can go to this say joints, columns, beams, and deselect it. Okay. Or say this braces, null lines, deselect. Okay, null. Then yeah, these are the frames. So to deselect that will be done.
Understood.
Okay. Okay. So now coming back to the 3D view. Okay. So yeah. So before we go into the seismic analysis, okay, I think we need to apply the dead and the live loads first. Right?
Yes.
So one thing I'll just tell everyone is that in this, if you go to define window, okay, and go to the load patterns, Okay. In this defined load patterns, you'll see that for the dead load type, there is a self-weight multiplier 1. So what this means is that the self-weight of all the elements will be taken care of intrinsically. It will be taken care of by the software. We
Correct.
don't have to apply them externally. Okay. So this dead load will be only, I want to keep this particular dead load only for the, say, the self weights. So I'll change it into SW. Okay. I'll modify the load into SW. Okay. Now I'll have some other dead loads. Say I'll be having partition loads. Sorry. Partition loads. Okay. Then I'll be having, say, screed loading or screed loads. Okay. Then I'll be having a terrace life. I'll keep the terrace life separate. I don't want to include that in the seismic analysis.
Right.
Okay, I'll use that as can go with either roof live or you can keep it simply live. Okay. Just one thing has to be kept in mind. This self-weight multiplier should not be repeated in the other loads as well. Otherwise, you'll be having 2 times the self-weight or 3 times the self-weight. You'll be getting erroneous results. Okay. So in the other dead loads, we need to change the self-weight multiplier to 0. Okay, so now we have dead, we have live, we have partition loads, we have speed loads, we have terrace live. Fine. So I'll keep one live as less than say 300. Okay. And I'll keep one live as greater than 300. This I'm doing, maybe the students can understand in the next step. Okay. Just because to change the participation factor for the live loads. Okay. Okay, so now we have defined the load cases, right? I'll press OK. I haven't defined the seismic load as of now. I'll first apply the dead loads and the live loads. Okay, so story 5 will be terrace. And okay, one more thing I have missed over here. There might be a machine room on top of the lift. Okay, so that I have not modeled. Right. But I would hope the students to model that in the homework. All right. So
they have to give slab then above, and then above the slab they will give say 2.8 meters or 3 meters long.
Yeah, machine room.
As they give stairs and Mumty like that.
Yeah. Okay. So I'll give parapet loads over here as partition loads along the exterior of the roof. I'll select the exterior beams. Okay. Then go to assign. Assign. I'll be going to the 6th menu frame loads and the 2nd distribute. Okay. Now this will be partition loads. And it will be a uniform load of say 3 kilonewton. Okay. Okay. Now in the previous class, we have not seen how to assign slab loads or say membrane loads over here. Okay. So we need to first do is select all the slabs over here. Okay. We need to select all the slabs where the loads will be applied. We'll go to assign. Just below the frame loads, there is a shell loads option. From the shell loads, we'll go to the second one, that is uniform load. And this will be, I'll apply say screed loads for roof treatment. Now you see the direction of the load is gravity. The gravity, as I mentioned earlier, will be negative Z direction. Okay, so if you have gravity, you can apply that for all the dead and the live loads. Okay, so I'll be giving say 2 kilonewton per meter square. Okay, or 200 kg per centimeter square for the roof treatment loads. Okay, just hang on 1 second. I'm getting a important call.
All right. No issues.
Yeah. Okay.
Please go ahead.
Yeah. So I'll apply the screed loads now. This is pretty simple. This is not very complicated. Okay. Now there is another option. Like say I had made a selection of the slabs earlier. After I applied the loads, the selection is gone now. Okay. So there are some options over here in the left ribbon. Okay. That will uh, make the process much easier. We have this all select all button. We have a PS button, that is get previous selection. What I'll do is I'll press that button.
Select previous.
Okay, so the previous selection gets active again. All right,
Okay.
now I'll apply the terrace life. Say apply 1.5 kilonewton per meter square as the terrace life loads.
Hmm.
Okay, so the roof loads have now been applied.
Hmm.
Okay. So just now we can go to the next floor.
Okay.
Okay, we'll go to the next floor. Okay, now what we'll do is
Your slab load weight will be anyways transferred.
slab
It's
load,
not like
your dead
it's
dead
unlike
load.
the floor load option which we use instead.
Yes, it is similar to that. I'll show you how it gets distributed. Okay. Before the analysis, you won't get the idea how it is getting distributed. Okay. Once I do the analysis,
Then
ETABS
one
will
way
show
to
you
look at
the
the distribution.
distributed area distribution. Okay. Okay. So I'll again select the floors over here. Okay. Now this particular floor, I'll keep it as say live
Keep it
greater
typical
than.
for all 4, 3, 2, 1. Let's keep a typical load for all 3, 4, all other stories. Will make our life easier.
Okay. Fine. I'll go to say now this has been selected. I'll keep it as 3 kilonewton. Okay. Now, say the flow loads are typical. Okay.
Mm.
So there is another quick way of modeling all the loads.
Mm.
Now, say I want this 3 kilonewton for all other slabs. Okay. So I'll close this window. Oh, sorry. Before I do that, I'll assign the
Mm.
screed load.
Mm.
I'll go to screed load. Screed loads will be say 1.15. Okay. So now I'll need to repeat this exercise everywhere. So what I'll do is I'll get the previous selection, go to the replicate command that is just below this interactive database.
Mm.
Okay. And now there is this story option over here. So this was story 4. I need it in story 3, 2, and 1. So I'll select it and I'll do an apply. Okay. Okay. Now you see that these loads here are not coming.
Mm.
Okay. Normally what happens is when you apply the loads and anything like that, the load gets transferred to the other replicated loads. Okay. There are now some replicate options that you need to explore. Okay. We'll go to edit again. Replicate, modify or show replicate option for assigns. I'll open it. Now in this shells, okay, you will see that uniform load sets. Okay, turn on everything. Okay, now what I'll do is I'll remove the slabs from here that I had drawn
Okay.
earlier. Okay, and I'll and I'll just replicate them. Okay, I'll go to slab sections. I'll select S150. Okay, all the slabs are being selected now. Okay, I'll just deselect the slabs in story 5 and story 4. So I'll go to deselect. I'll go to stories. Okay, I'll deselect them and then delete. Okay, so this selection process everyone is following.
Yes.
Okay, all right. So again, what I'll do is I'll just I'll select the S150 slab.
Maybe what we can do in 2 stories, we can replicate 1 story because we were trying to show live load more than 3 also, no?
Yes,
So
yes,
it will
yes.
remain all line.
Yes.
So in 2
Okay, then
stories,
the
we will
last,
replicate in 1
what I'll
story.
do
We'll
is
have
one story I'll keep as class
more
3
than 3.
loading, another will be more than 3.
Yeah.
Okay,
Yeah.
so right, I'll go to now stories. Story 5 will be deselected. Close it. Control R, and I'll keep story 3. Right now, if you just right click
That's
over here, you will see that the loads have been transferred.
correct.
Okay. Now, for this floor again, I'll just do a previous selection. Get previous selection and make this story 2 also.
Replicate.
Yeah. Okay. Now previous selection. Okay. Sorry. Okay. Now I'll come to story 2 where I need class 5. Okay. So now what happens is, say if I select, if I make a left to right window over here, at the bottom left, you can see that a number of frames, joints, and shells have been selected. Okay, so while modeling here, we don't need to worry too much about the load application. Okay, when say when we are assigning shell loads, if frames and joints are also selected, okay, the load will not get assigned to them. The load will only get assigned to the shells.
Understood.
Okay, so we'll go to assign. We'll go to shell loads. Go to uniform. Right, street load will be the same. Okay, now here one thing needs to be done, that life less than 300, it is already there as 3 kilonewton. I'll change it to 0 and see here that the replace existing loads command as button has been ticked.
Correct.
Okay, so now if I'll apply it, your live 300 load will be 0. Okay, I'll get the previous selection again. And now I'll apply live greater than 500. Okay, I'll apply 5.5 kilonewton per meter square. Okay, so applied. Right. Okay. Okay, now before I go there, we need to change the support, the base support conditions from hinge to fixed. So again, I'll go to assign joint. The restraints will be fixed.
So it will create restraints for shear wall also.
Yes, we create restraints for the shear wall as well. Okay, so now we'll delve a bit into the say. Okay, there were some other commands that that was remaining, right? Um, okay, I'll do one thing. I'll show how the mass source is defined and the seismic loads for the static case, how they are defined. Okay. And then we'll do the minor edit commands that was remaining. So okay, so we'll go to define now. The fourth window, define, and we'll come to load patterns. Okay, now here we'll be having a load type of seismic, and say I'll be defining EQ EQX. Okay, auto lateral load will be IS 1893 2016. There are various other codes also available here. Okay, so I'll add a new load. Okay, then I'll do EQY, add a new load. Okay, now now the loads have been defined, but I need to modify them. I'll go to modify lateral load. Okay, now this IS 1893 2016 window pops up over here. Okay, so here the first portion here shows us the direction of the applied load. Okay, so we'll be having loads in along the x direction only, right? So we'll turn off the other ones over here. Okay, right, and the story range will be from the base to the roof. Okay, we can change it as per our wish. Then the response reduction factor as per IS 1893, depending on the ductile detailing and whether the structure is ductile detailed or not, it will be 3 or 5. Okay, depending on the type of structure. Then we have the seismic coefficient over here. The seismic coefficient can be either say 0.36 for zone 5, 0.24, 0.16, or 0.1. Okay. We also have user-defined seismic zone factors. Okay, so we'll go as per code and make it as zone 4. Okay, now site type is actually for the soil factor. Okay, this is for the soil factor. Okay, 1 is for very hard soils, 2 is for medium soils, and 3 is for soft soils. Okay, and then we have the time period over here. So if you click on the program calculated button, what will happen is before we do the before we do the dynamic analysis, response spectrum analysis, the program automatically runs a modal analysis where the fundamental time periods are found out from the data that we are given in the model. Okay, and those time periods are taken up here. Okay,
not as per the code.
No.
0.09 under root h by d. Those formulas don't use.
Yes. So we'll go to user defined. Okay. So in user defined, what we'll do is we'll be having the height of the structure over here. Okay. And we have the
calculate basically.
We have the so for x, say x direction, we need this d over here. Okay, which is dx. We'll be needing that. This is I think 32 meters, or no, it is I think 32.15 meters. Right. So we can just directly write here the height is 14 meters. H divided by d is 32.15 to the power 0.5. Okay, so you have a time period over here. So some of the forms here, they have this inbuilt calculator. Okay, not all. Okay.
This is good.
So this importance factor, that will be as per the code. I'll press OK. So X seismic force along the X direction has been defined. Okay. Next will be seismic force along the Y direction. So again, modify lateral load. I'll turn off the seismic forces in all the other directions. Right.
Although it would have been 32.3. 150 offset is from both sides. No? It's okay.
Yeah. Taken it from here. 32.15.
Yeah, from it would be both sides offset, no? 150.
Yeah. So 150 mm from here.
No issues. That is minor.
Okay. So then, all right. Where was I? Yeah. So Y direction here. and your story range is from base to thing. Again, same form here, only direction will be different. The seismic zone will be as per the project. We have the site type and then user defined. Okay, so we have 0.09 into 14 divided by, so this dimension we have 32.3.
32.3.
Yeah. Oh, sorry. So this will be 0.09 into h divided by 32.3 to the power 0.5. Okay, so we have the time period as well. Okay, now there
Where
was some,
eccentricity option comes.
yes, we have the eccentricity option also. I didn't show
So where
that.
do we apply that?
Here, it's better to apply that. Like if we say we don't have information prior to the analysis, whether there is some eccentricity or not, although we need to apply 5% eccentricity
Mhm.
As per the codal provisions. So that can be done here. Okay, so I'll define one, say EQX positive. Okay,
Okay.
I'll add a new load. I'll go to modify lateral load. So we have X direction plus eccentricity. So I'll turn off all the other things.
Mhm.
So eccentricity ratio all diaphragm. Now we haven't come to the
Define.
diaphragm part as well. Okay, so maybe in the next class we'll do that. Okay,
Okay.
so just to keep it in mind, this eccentricity ratio will be 0.05 as per the code. Right, this is for the accidental thing, eccentricity. Right, so this will be the same again. Everything else will be the same in this form. We'll be having the user defined thing over here. We'll be making it again. We'll be doing the same exercise over here. Or the
0.22.
yeah, we can keep it as 0.22 for the time being.
Yeah.
Okay. Similarly, this can be done for X negative. X negative,
Take
the
minus
X
5.
direction minus eccentricity. Everything will be remaining the same.
अरे कौशल सर पूरे हस्बैंड समाज में डर का माहौल है
Okay.
Okay. Then we have this Y positive. Okay, modify lateral load. We'll be doing Y positive over here, 0.24, 0.22. Okay, so Y positive, then Y negative. Okay, so we have defined the seismic, the static forces for the seismic. Oh, the forces for the static seismic analysis, right? Pseudostatic. So, okay. Next, once this is defined, we'll go to define again, and the mass source needs to be defined now. Okay, for the mass sources, we'll go to modify mass source, modify or show mass source, or we can add a new mass source. All right. So I'll add a new mass source over here. So I'll name it as, say, MS. Now from here, we'll switch off the element self mass and the additional mass. We can even model additional masses as well, but we'll not be doing that currently. We'll be doing it from specified load patterns. Okay, so we have the dead self weight. We'll be adding that. The multiplier is 1. That is the full extent of the dead load. Then we'll be taking the partition loads as well. We'll add that. We'll be taking the screed loads as well. We'll be adding that. Then we'll be taking the live less than 300 as the multiplier will be 0.25.
Okay.
And live greater than 500 will be having multiplier as 0.5. Okay, so we have 1, 2, 3, 4, 5 things over here. Anything left behind? No. Okay.
For roof, we have to again define mass source.
Roof will be leaving out because that is not required for the
Okay.
thing, right? Okay. Now include vertical mass. This say this will be required in the dynamic analysis, right? So what I'll do is I'll currently keep this thing ticked on.
Okay.
Okay, I'll keep it ticked off currently. Okay, because it might give some errors. All right. So I'll just tick it off currently. Okay.
Vertical mass is for the third combination.
Yes, yes. For the third combination.
1/3 of the acceleration.
Yes, yes, yes.
E
1 by
vertical.
3. Yeah, yeah. So this is my mass source. Okay, MS. We need to keep that in mind. So I'll press OK now. Right. So now my static thing has been defined.
Mhm.
Okay. Static earthquake load has been defined. Okay. So now I'll limit my seismic portion till here. Okay. There were some things that were left in the edit command.
Okay.
Okay. That will be required in this exercise, the homework that I've given.
Okay.
Okay. So what I'll do is I'll go to this plan view, go to story. Well, I'll just go to any story, say story 5. Now we can model curved beams in ETABS. Okay. So for modeling curved beams, there is this function called this modify or show frame type. Okay. Now you see this is not active currently because we have not selected any frame.
Okay.
Right. So what we have to do is first we need a frame. Say I'm drawing a frame over here. Okay. Now here what we'll do is we'll go to edit. We'll go to frames. Okay. Now see here there are some 5 functions over here. One is divide frames. Divide frames I think we had discussed earlier. Join frames is also the same. Okay. Now convert beams to slab areas. All right. We can also draw slabs in this fashion. Okay. In some cases, it's required. So say if I have this beam over here, okay, and I just press this command, it will be converted into a slab. Okay, of width 300 and depth 600. Okay, this was a 300 by 600 ka beam. Okay.
Achha.
So I'll just undo this. Select this type over here. Go to edit.
So this is used to make, say, a frame element into a plate element kind of
Yes, yes, yes.
conversion.
Yes, something like that. Can be used for even this in flat slab designing
Flat
or
slab design.
modeling flat slabs. Okay. All right. So edit frames, and then we'll go to modify show frame type. So modify show frame type. We have this. We have the story over here mentioned and the label of the frame. Okay, that is B40. Okay, so frame type now is straight. All right. ETABS gives us some like this curved options like circular curve. It gives a multilinear curve, a BZ curve, and a spline curve. Okay, as per the requirements of the project. Okay, these functions can be used. So I'll currently focus on the circular curve. Okay, so in this circular curve, what we need is we can draw a circular curve from here. Okay, by 2 methods. One is if you have the radius, all right, and on which side is the radius, the center point, okay, and which side is the curved side of the line, okay. So like say if you have this, I had drawn this frame from here to here, so this is end I and end J. End I and end J needs to be kept in mind. Otherwise, just right clicking it will also give us a sense of that. Okay. So if you have the end I, so end I, the left the center point on this side of the line. So left will be this side and right will be this side. Okay. So we need to specify say a radius of say 3 meters. Okay, and no, sorry, I'll keep it a little more, 15 meters, and radius on the left side, and the curve will be on the right side. So refresh window, we'll see a curve over here. A circular curve will be created. Okay, this is one way of having modeling a curve. Or else, if you have some coordinates, say if you have the first coordinate, if you have the say the end coordinate, okay, and if you have a third coordinate, okay, third coordinate can be this apex point. Okay, if that is also available, we can model a circular beam. Okay, so now once your circular beam is modeled here, okay, we need to break this into multiple smaller segments. Okay, so that the analysis results can be proper. Okay, we'll divide it into, say, as per your, it will depend on the curved length. It's better to have, say, 1 meter for a longer span beam.
But then
Say 1
aspect
meter or a
ratio
point.
issue won't come. L by D ratio.
No,
is
that
very
won't
short.
come. That won't come. That won't come. Okay. So I'll divide it into 8. Okay. So now it has been broken into 8 smaller segments. Okay. So this will be required in the homework that I had given. All right.
Then
Okay.
that can be edited and kept it at the desired location.
Yes, it can be edited and kept at the desired location.
That is, moving command is also there in edit.
Moving command. Yes, we can move that as well. Say I need to move this. You can go to edit. Okay, we'll have move joints of frames shells. Now X, say I move it by 5 meters. Okay, will be moved like that. Or else we can pick points from the model.
Okay.
And it will move. You just have to do the previous selection. Okay.
Picking and putting.
Yes, and then there is okay. There are some other views, some other commands also. One is this view command. Okay, in this view menu, there are some. I think last time I had not touched up on this set elevation view. Okay, so set elevation view, you can have actually say the you can have the elevations along the predefined grids. Okay, or we can have it at some ordinate as desired. All right, so what I'll do is first let's see the elevations along the A and along the grids that we have defined. So these are the elevation views. Okay, I'll go to 3D again. Again, go to view. Okay, and there is this. We can even set plan views at some intermediate levels. Okay. I say at we have defined the floors, right? But we can have a plan view at some intermediate level, say at
11.
At say 3 meters. We have the first story at 2 meters, so 3 meters will be in between. We can have it here. Okay, so you can see how it is, how that floor is, how that region looks in plan.
Slab won't be seen.
Yeah, slab won't be seen. Okay, neither any beams. So this is another function that is available in the plan view. All right.
Can we see it with all the dimensions so that we can directly take a model into PWG?
Okay, say dimensions here, it's there. Okay, do you want to see the section sizes?
Yes.
Section sizes. Okay, for
with section sizes so that yeah, it can be imported to CAD.
Okay, section sizes say I have this set display options. Okay. I'll go to object assignments. Okay, we have this frame assignment sections. I'll press OK. And we have this.
Okay.
Okay. So we whatever sections we have defined, that will be visible over here.
This
Right.
whole thing can be then exported also.
This can be, you can export it as a DXF or DWG file. Yeah. This can be done. Okay, this
The
plan
same
view.
view, this view, which the view which we have
Not the exact view. Maybe you'll get some view in the CAD version. Okay. But if you want, say this, if you want this as an image, you can always take that. Okay, you have this capture picture over here. You can have the entire screen of the main window or the current window as DXF or DWG. Okay. So current window as PDF. All these things can be done. Okay. And yeah, there is another thing, view building limits, set building view limits, right? Now say the structure is having different plans as we along the height. So we can view it, say we are viewing the whole structure over here. We can view from say story 3 to story 5. So you'll see that the lower portions will disappear. Only story 3 to story 5 will be seen. Okay, you can also play with the minimum and the maximum along the x and the y axis. Say we can view it up to say 10 meters over here and say 5 meters over here.
Right.
Okay, so we'll have something like this. Right. So, and if you want to view the whole thing, show all. Okay. Okay.
In all the boxes, we need to show all.
This will be 32. This will be show all here.
Show all.
Yes, and we'll have the entire structure over here. Okay. So this is another command over here that I had to mention so that your modeling can be simpler. Okay. So any questions from today's class?
Students, if anyone has any doubts from this session.
Today, I think we have ended at mass source.
Yes.
Okay. So I would like the students to develop the model that I've sent. Okay, the drawing that I've sent. Okay, I want them to develop it up to mass source with the with all the seismic pseudostatic seismic forces defined. Okay, then we'll go into the say the analysis of the pseudostatic seismic.
Simple gravity analysis we have not shown. No? We can show.
Okay, gravity analysis we can do now. Okay,
yeah, we can do that.
We have the model
loads
ready.
we have not applied.
Yeah, we have the model ready now. Okay, so what we'll do is we'll go to analyze. Okay, we'll open the analysis menu over here. First thing we'll need to do is check model. Okay, select all. Okay, we should check whether we should check whether the everything has been joined properly or not, whether there's any overlap. Okay. So if it's okay, then we'll go to
null members. These kind of warnings it gives, no? If there are null members or
if something is overlapping or something is too short, okay, it'll give those errors over there. Okay. Now what we'll do is we'll go to set load cases to run. Okay. Now currently what I'll do is I'll turn off the modal analysis. Okay, we can turn off load cases as we feel necessary. Okay, I'll turn off the modal case. Then I'll do is I'll turn off the pseudostatic analysis case. Okay. All right. Now what I'll do is I'll run.
And there are any processors to be chosen from in this run command?
No.
Non-linear modeler or solver.
No. Not for this currently. Okay.
Oh.
Run now. Okay, so what I'll do is I'll define. Okay. So now we will see the window that is in front of us is the displacements for the dead loads. Okay. We can now after the analysis is done, there are a lot of results in front of us. Okay, we have this show deformed shape. We have display support or spring reactions. We have the display frame or the spear or spandrel forces, and we have the shell stresses. Currently, only the wall is a thin shell element, so shell stresses will not be of much use currently. But we can see one thing here, like I had a display shell load asides. We had like defined the loads for the dead loads for the on the membrane, right? The screed loads and the what do you say, the
Live loadings.
Yeah, the live loadings we had mentioned here. So that can be viewed like what is the portion of such loads being transferred to the say the
Tribute
frame.
table.
Yeah. So all loading that is we'll have to go to show frame loads. The load pattern will be say screed loads, and all loading that is tributary to the frame object or forces. I'll just go apply. Okay, you can see here. Okay, now there are some ways. Now, in some portions where there were one-way slabs, we can define.
Yeah, triangular
that
kind of shape will be able to
Yes.
see, and for
Yeah.
two we'll be able to see trapezoidals.
Yes. Okay, so this is the screed loads. Or similarly, we can view the other loads that we have defined, like the live loads less than 300. Then we can see the live loads that are greater than 500. Okay, and we can also check the terrace line.
Okay.
Okay.
This is the distribution, how they have been distributed.
Yes.
Now coming to
Okay, so
results.
Okay, so I'll now turn off the show undeformed shape. Okay, now to view the bending moments, before I go to bending moments, we can see the support reactions as well. So I'll press on display support reactions. Say we have the dead case over here. I would like to view the FZ, the FY, and the FX values, and say also the moment values. Okay, so that will be shown here. For better viewing, we can always go to the plan view, go to the base. Okay. So here we have, if you just take the cursor over here, you can see what are the forces coming here. Fx as 4.6753 kilonewton, Fy as minus 14, and Lz as 580.015. And the moments are also being shown here. Okay.
Minus
So-
14 is FZ is positive.
That is these forces here are based
Global
on the
axis.
global axis. Okay, so minus Fy will mean it is acting
Swinging.
along this direction.
Oh, yes.
Yeah. Okay, and Fz means it is a positive Z direction, that is upward reaction. If we have a minus Fz, means it is
Uplift must not be there.
yes.
So negative force won't come.
Yes. So
Because
that
we
has
are
to be checked.
only doing gravity analysis.
Yes, that has to be checked. Now, sometimes even there might be some mistakes while modeling, like some beams may not be attaching into the column, or say a secondary beam might not be framing into a primary beam. That
Mm.
time you may not get an what to say an unstable structure, since this is an indeterminate structure. So you can always view that by checking the deformed shape.
Mm.
Okay, you can go to the case over here, right? And you can do the scaling as you wish. All right, and you can check the start animation. So you do the start animation, you can see how the structure will behave for dead loads.
Mm.
Now, if you detect some deflection which is not
Not
as per
coming in
your
certain.
not as per your engineering judgment, you can always revise the modeling of those junctions, right? And you can check the behavior of the structure also through this. Yeah, I have magnified the deflections to a great extent. You can see that the secondary beams with the moment releases, they are vibrating a lot because their joint rigidity has been removed. So they are acting like simply supported beams, while the others, they are behaving normal. They are behaving like normal rigid frame structures,
Yes.
right? Okay, so we can check the display. We can check the member force diagram for the frames by clicking on display frame or pier or spandrel link or link forces. Here, as per the load cases, we will be having the forces like axial force, torsion, in plane shear, shear along local axis 2, moment along local axis 2, in plane moment, shear along local axis 3, and moment along local axis 3. All right. So now let us get an elevation view of say grid A, right? And let's check the M33 moments. Okay, you can see here the moments have already been done. The moments for the beams and the columns, they have already been done for the connection, for the intersection of the columns and the beams.
So red is hogging and
You
yellow is
can
sagging.
say if you need to view one of these diagrams individually, you can always right click on them and you can check you can check what are the loads coming on that particular frame, what is the shear force, then the bending moment diagram, and also the deflection. And you can scroll along the length to view the values that are changing in the right hand side corner of the diagram. You can check at what section you are getting those values, or you can just click on show max to get the maximum values of say deflection and your bending. The bending moment here is shown here. The negative bending moment here is the maximum. That is at the column and beam intersection. Okay, you can view the major shear force. Like V2 is the vertical shear for the beam, and M3 is the
bending in the
major
direction.
bending. You can also view the minor forces over here.
They will be very less.
And we can also view the torsion and the axial force. Okay.
And these reports can be generated into a written form also.
Similarly, we can view them for the other load cases as well. We can also view M22 diagrams if we feel like.
For beams, they won't come.
Okay, we can change the type of viewing. We can also, view them as contours over here. We can view them as contours as we deem fit. And you can see the values of the bending moment varying for different colors. can view the axial forces from here. I'll turn off the show contours. You can check whether your engineering judgment is being validated through the results.
So on shear wall, we are not seeing any forces currently.
Okay.
Is it only showing on the frame structures, not showing on the shell
So these
structures?
results can also be obtained in a tabular format as well. So that you can take these values and work on some Excel sheets that you have. Okay, it's better I stop here. Otherwise, it will take. I'll again exceed the time limit over here.
Sure.
Okay, so
we'll see about results and how to export them in tabular
next class
form,
we'll
or how
touch upon the seismic analysis, the dynamic as well, the static and the dynamic. And before that, I would like all the students to work on the homework that I have given. And if they have any doubts, we can clarify it in the next presentation.